All right, everyone, welcome to the AI Research Roundup. I'm Alex. Today, May 8th, 2025, we're looking at an ICLR conference paper. Predictive Inverse Dynamics Models are Scalable Learners for Robotic Manipulation, published January 22nd, 2025, so a little over 3 months ago. This paper introduces Predictive Inverse Dynamics Models, or PIDM. It's an end-to-end way for robots to learn manipulation, meaning the AI learns to connect seeing with doing, all at once. The model, Seer, forecasts future sights, then uses a transformer architecture, a powerful AI model, and inverse dynamics, which is like figuring out actions for those predicted scenes, to decide its next move. So this first figure really sets the stage. It contrasts their predictive inverse dynamics model approach, specifically the Seer model, with older methods. You see, traditional behavior cloning, that's where the AI just copies demonstrated actions, and two-stage systems, which handle visual prediction and action planning separately, are shown next to Seer's integrated design. This design is first pre-trained on large robot datasets, then fine-tuned for specific jobs. And the bar charts on the right really highlight Seer's superior performance over previous state-of-the-art results. That's the best performance seen before, across different benchmarks. Okay, so building on that impressive performance, this next figure really unpacks how Seer operates. We see its pipeline, starting with a multimodal encoder. This part processes diverse inputs: the current RGB image, that's a standard color photo, language, and the robot's state, plus special foresight and action tokens, which are like internal data cues. Then, conditional visual foresight predicts future scenes. Critically, the action token uses this foresight, thanks to unidirectional attention, allowing the inverse dynamics prediction to then determine the robot's actions. This tight integration is key. Alright, so this table really gives us the numbers to back up Seer's capabilities. It's showing results from the Libero-Long benchmark, a set of challenging, long-horizon manipulation tasks, meaning tasks with many steps. We see different methods, including Seer and Seer trained from scratch, compared on their average success rate. This rate is across 10 tasks, averaged over multiple rollouts. Those are test runs, using top model checkpoints, saved AI training stages. And Seer, the pre-trained one, clearly comes out on top with an 87.7% average success, outperforming other baselines, existing methods, on most tasks, as shown by those bolded numbers. So after seeing those strong success rates, these next graphs really dig into Seer's data efficiency and how well it scales up. The two-line graphs on the left show performance on both Libero-Long and Calvin ABCD when using different proportions of downstream data. That's data for fine-tuning on specific new tasks. We can see the pre-trained Seer consistently achieves higher success rates or longer average task completion lengths, especially when there's less data available. And then, the bar chart on the right illustrates that as Seer's model size grows, indicated by more trainable parameters, which are the adjustable settings in the AI, its average task completion length on Calvin also gets better, especially when pre-trained. Okay, so drilling down further into those Calvin ABCD results we just touched on, this table shows us something quite interesting. It details how many tasks different models can complete consecutively, all the way up to 5 in a row. And that AVG, Len, column, that's the average number of tasks successfully chained together out of 5 attempted. You can see Seer Large, especially the pre-trained one, leads with an impressive average of 4.28 tasks completed, setting a new state-of-the-art for this challenging benchmark. So, to understand why Seer performs so well, this table presents ablation studies. These are experiments where components are removed to test their importance. It examines the training objectives used during fine-tuning and pre-training, specifically the conditional visual foresight objective, L_4, for predicting future scenes, and the inverse dynamics prediction objective, L_INV, for determining actions. And clearly the data shows that integrating both these objectives, whether for fine-tuning on new tasks or during the initial pre-training, yields the highest average task completion length, really underscoring their combined value. Building on that understanding of the training objectives, this next table shifts our focus to real-world performance. It's Table 4, showing the main results from actual robot experiments. We see different methods, including Seer and Seer trained from scratch, evaluated on 4 tasks like flipping a bowl and stacking cups. The columns show success rate, or senior, which is the percentage of successful attempts, and a general score. Across all tasks, and particularly in the average, the pre-trained Seer achieves a significantly higher success rate of 78.4% and a score of 39.5, outperforming the others. Alright, those compelling real-world results really underscore the main message. The researchers introduced an approach called Predictive Inverse Dynamics Models, or PIDM. These predictive inverse dynamics models essentially involve training the AI to both predict what things will look like in the future and, based on that, what actions the robot should take. This integrated approach allows Seer to achieve remarkable performance and adapt impressively, even when data is scarce. It's a big step for scalable robot learning. Thanks for tuning in to the AI Research Roundup.